Hello everyone, welcome back to my channel. My name is Chacha, and today I'm going to be going over the fifth chapter of the chemistry textbook for the MCAT, which is chemical kinetics. Quick disclaimer that I like to do before I start any of my videos is that I too am a student studying for the MCAT, so there may be mistakes, but feel free to point them out in the comments. Okay, without further ado, let's get started. Um, so first things first, before we kind of dive into a deeper thing, is to go more into the definitions. So what is a reaction mechanism? So it's almost never is a balanced chemical equation. What do I mean by balanced chemical equation? I mean the stoichiometric balanced chemical equation that we went over in chapter 4. So that's saying like 1 mole of A plus 1 mole of B gives you 1 mole of C. It's almost never the orders or the exponents that you'll see when we go over the kinetic equation. That is almost never these coefficients in front of the concentration. You need lab data in order to figure out the order slash exponents. And that's really important to keep in mind when you look at these equations. Or like when you're given a problem, you need lab data. You can't just be like, oh yeah, it's gonna be like because that number in front of like uh molecule A is 1, it's gonna be raised to the power of 1. No, that's not it. It's a trap. Um, Many reactions are multiple steps, but we only consider the rate determining step. So this is like very similar to what we saw in the last chapter with the limiting reagents. Think about the rate determining step, sort of like a kinetic bottleneck. Like the reaction cannot occur faster than it, similar to the limiting reagent. The reaction cannot occur past like how much of that limiting reagent you have, like or how many moles, I should say, of that limiting reagent you have. It's the same thing with this, except for it's time slash speed instead of amount or like moles of the product. Sorry, reactant. So it's also known as a slow step. Um, so here I kind of have an example. So I have A subscript 2 plus 2B leads to, or the product, or produces, I should say, 2AB. That's our product. So step 1 is our slow step. So this is the step that is like, will be the kinetic equation step, whatever that may be. And I'll kind of get into more what the kinetic equation is in a little bit. So step 1, you have A subscript 2 plus B gives you A subscript 2B. This is going to be an intermediate A subscript 2B because notice in step 2 that this is a reactant now instead of a product. So it's A subscript 2B plus B gives you 2AB. And this is the fast step. So it's an intermediate because it's only included in the subreactions, not the overall, due to it canceling out, like sort of like canceling out. I mean, like, look at it, it appears on the products and reactant side, so that means that it's as fast as it's produced, it's used up to produce the overall product, which is 2AB. So I have this little sum symbol here. So A subscript 2 plus 2B is equal to 2AB, because if you cancel these out, that is your overall equation. Also really quick, I want to go over collision theory, which is kind of the basis of kinetics or like kinetic equation, like how products are formed from reactants. So that not all collisions result in a chemical reaction, so that's really important. Otherwise, you'd have like an insane amount of, I guess, product, or like it would just appear like, I guess, like instantly, I guess, more or less, I should say, which is not what happens. So what does result in a product from two reactants? The first thing is correct orientation. So notice here, this blue molecule that I have and this green molecule I have, this kind of red dot implies that they need to be aligned, like it needs to have that correct orientation in order to form a product. And if you could see from their path, which is indicated by this yellow arrows that I have, they aren't going to line up. Whereas here, these red dots line up perfectly, which means that they have the correct orientation. Also, you need the correct energy to break and reform bonds, also known as activation energy. So activation energy is essentially from your reactants, or that this is a reaction coordinate. If I could find my pen. Reaction coordinate, and this is Gibbs free energy here. So basically this is a reactants. and this is the transition state. So it's basically the difference between the transition state and the reactants is your activation energy. So you need the correct energy to break and reform those bonds. Yeah. Um, Here are kind of the components that go into the rate constant, which is also okay, but it's not a true constant. We'll get to that in a little bit. So the rate constant and the Arrhenius equation, which you don't need to memorize, just kind of know the patterns. The rate constant K is equal to the frequency factor, so it's the number of collisions that occur. Euler's times Euler's number, or E, raised to the power of the negative activation energy over R, which is ideal gas constant, times T, which is temperature. It's kind of looks complicated, especially when you get into like E, logs, all that sort of stuff. But it's not really like when you get into it, like when you think of like the natural world, like what you know about chemistry, like biology, like physics, what you've learned in your classes. It's not that complicated because basically, it's saying as the frequency of collisions, or A, increases, so does the rate constant, which makes sense. So it means that you're going to have more products formed. This is a direct relationship. So essentially, this is saying, how do you increase the number of collisions? Well, that makes sense. If you increase the concentration or the amount of molecules that you have, you're going to increase the frequency of collisions. That makes sense. If you have more molecules, the chances of them hitting one another at the right orientation is increased. Also, if you have a particular medium, some molecules prefer different mediums or they're more likely to collide with one another instead of the medium. So you could have an aqueous, polar, nonpolar, etc., medium. Also catalysts. Catalysts can reorient substrates, which increases the frequency of the correct collisions, which can actually decrease the activation energy. Um, yeah, so kind of what I have over here is I have this reaction coordinate with increased activation energy when there's no catalyst. So it's like a really big mountain or hump or hurdle, whatever you want to call it, to overcome. Whereas if you have a catalyst that actually reorients the chemical or compounds in a way that makes it easier for them to collide correctly, it decreases the activation energy. It's easier to reach that transition state. That's also another way you can think about it. Really important thing to keep in mind for catalysts is that they don't actually change your final gives free energy or your starting gives free energy. They only change the transition states gives free energy. Also, it makes sense that as you increase temperature, so does the rate constant. It increases because you're adding more energy. I guess temperature is kind of a proxy for kinetic energy. So, like they're moving faster, so that means that they have a higher chance of running into one another. But this is up to a certain point, because after that point, then you could start to have adverse effects such as like denaturing of proteins, and stuff like that. As That's kind of what I already said. So like as you increase the activation energy, your rate constant's going to decrease, which makes sense. Going back to over here, right? If you have a really high hurdle to overcome, then chances are your molecules aren't going to be able to overcome that barrier very easily or often, I should say. Uh, it's just like if you have like a small hill to overcome, like if you're like walking up a small hill compared to like climbing Mount Everest, right? Only like super like complicated or like in shape people who have like trained for that mountain for forever are able to climb Mount Everest, whereas like anyone can climb the hill. That's kind of what the activation energy is saying. One more theory. I know there's a lot of theories in this chapter, but that's the transition state theory. So, we kind of already talked about the transition state when I went over reaction coordinates briefly. So, it's an in-between state where old bonds are still there while new bonds are being formed. So it has the greatest energy due to the sheer amount of bonds. Bonds you could kind of think of a proxy, for like enthalpy or just like energy in the reaction. So either forms products when she reaches transition state, which is like at the peak of this mountain, or it goes downhill, and then at least in the forward direction it goes downhill, I should say. Um, or it can go back to the reactants over here. It can go either way. So forward, as you can see here, It's an exergonic reaction, not to be confused with thermic, since thermic is exothermic is a term used for enthalpy. Anytime that you see therm, think of like thermal energy, uh, which is related to enthalpy. Exergonic, which exerts energy. So your final minus initial products is a negative, whereas your reverse reaction here, it requires energy because the final minus initial is a positive number. And you kind of think it makes sense that it's maybe counterintuitive, I guess I should say at first, when something that's negative is actually like spontaneous, or something that's positive is non-spontaneous. But it makes sense that if you have to add energy into a reaction, then it's going to be slower. It's not going to be spontaneous because you have to add that in. Whereas if you exert energy, that means that you don't need to have a lot of any energy added. It's releasing it. It's all like everything's all happy. That's kind of how I like to think about it, at least. Um, Now we can kind of go into reaction rates, and kinetic equations. So over here, remember again, like this is just something that you have to say reorient, or not reorient. I'm going to reiterate time and time and again is that you need when you're determining your reaction rate or your kinetic equation, you need to have the data for these exponents x and y, which are also the orders for the concentration A and concentration B, experimentally, not via stoichiometry, which is up here. So it wouldn't be x. This x wouldn't be like little a. It wouldn't be that. And b, or y, I should say, would not be little b. So let's reorient ourselves a little. So k is that rate constant. So it's the same rate constant that was in that Arrhenius equation. So here, and it's not a true constant because as Arrhenius equation dictates, that there's a numerous factors that go into it, like like that frequency factor of collisions, their activation energy, and your temperature. So if any of those changes, K, for that particular reaction will not be the same. There's only two scenarios where the stoichiometric coefficient is the same as the rate law exponents or order. The reaction is a single step, and the balance reaction is reflective of the whole chemical reaction, or the reaction mechanism and rate determining step are given to you, so they're known. This will pretty much almost never happen, but it's nice to believe, I guess. So K, the rate constant is not, as I said already, I guess. It's not a true constant like gravity on Earth, where that is always 9.8 meters per second squared. It changes when the components that make up the Arrhenius equation do, which I said already. Sorry, I jumped the gun a little. Um, Here is an example problem from the textbook. Basically, it's saying like find the rate law at 300 degrees Kelvin. So, remember the rate equation when you're kind of doing this? So rate is equal to K, which is constant at that temperature. And we're finding it for the forward reaction. So K, we have A and B. So we need to find essentially X and Y for these particular, I guess, equation that we don't have. And also K. So there's going to be a lot of plug and chug. Um, so step one is to choose two trials. Since we're trying to find that x here, that first x, so the order for A, I should say. So we're trying to, in order to do that, we need to choose two trials where the concentration of B is held constant. So just like any math problem, you can't have two unknowns. So because if B were to change, then like we wouldn't be able to find X. So trial two and three, B is held at 2. Its initial concentration, and molarity is held at 2. So we're going to look at trials 2 and 3, where the A, where how much does A change by? So it changes, it doubles, so it goes from 1 to 2. And then how much does the rate change? It approximately doubles as well. So the rate is proportional to the concentration of A raised to the power of X. So it's saying essentially since your rate is 2, that's proportional to 2 to the power of X. And where did I get this rate proportional to A to X? Because we're keeping B constant at this rate equation. It's essentially saying this, and we're um kind of like assuming we're not looking at k right now. We're just saying like rate is proportional to a to the power of x. That's what we're solving for. These two, let's just assume that they're held constant in order to find x. So yeah, that's where that came from. So basically x is equal to 1 because 2 to the power of 1 is equal to 2. Now to figure out the order for B, we have to choose trial 1 and 2, which has a constant A. So trial 1 and 2 here, notice how A, the initial concentration, is 1 and 1, whereas for B, it goes from 1 to 2. So that concentration doubles, whereas the rate is going from 2 to 8, so that quadruples. So over here, I have 4 is equal to 2 to the power of y, and y is equal to 2, since 2 squared is equal to 4. So now we kind of have our exponents for A and B. So we have our order. So this is a third order equation. But now we need to find K because our we're not complete yet. Our kinetic equation is not complete. So basically, you could just plug and chug. So you could choose any of these. I guess, values in order to plug in. Always choose the simplest one. So in this case, because these all have like whole numbers, trial 1 also when you have anything that is 1, that's easiest, you know. So basically I'm going to plug in my rate equation. So A will be 1 to the power of 1 and B will be 1 to the power 1 squared, I should say. And the rate is 2. So over here I have 2 times K. And I already said 1 to the power of 1, 1 to the power of 2. So it is k is equal to 2 molarity to negative 2 times seconds to negative 1. So there's our final equation. That is our kinetic equation for the values that were given to us. So overall, this is a third order reaction. And we're gonna get into what the heck that actually means. So overall reaction orders, this is like something that's not super important. You would probably just be asked to identify if you're given a graph what type of order this is. So zero order is a product formation, which is independent of the concentration of the reactants, since they're both raised to the power of 0. So that means that it's completely like they're the same. So it's completely dependent on temperatures and catalysts. Um, since if you raise anything to the power of 0, right, that is 0. So this is saying rate is equal to k. And this is a complete linear graph. First order is when you have a rate that is directly proportional to only one of the reactants, um, which is doubling the reactant like rate. So this is a natural log curve if you want it to be linear. So this is kind of like follows that natural log curve. Um, the second order is either reaction is proportional to individual reactants. So rate is equal to K, A to the power of 1 and B to the power of 1. So 1 plus 1 is 2, or 1 reactant squared. So K is equal to A to the power of 0 and B squared. And the inverse, so in order to get the linear graph, you just have to invert 1 over the power of A. That's kind of all I want to say. Third order is a little more complicated, so it's not really worth talking about in my opinion. Um, yeah, that's kind of all I want to say about chemical kinetics. Hopefully that made sense. Once again, my name's Cha Cha.